Okay, it's wonderful to hear all the enthusiasm in this group. Welcome. If you haven't been here for the series before, I wanted to make just a few comments as we begin. One of my challenges during this hour is I'm on a time frame. I have to stop, so I'm going to do my best to get what I want to talk about in the time frame that we have. So thank you for being here. What a pleasure. It's a joy for me. I wanted to tell all of you that were here yesterday. I did talk to Marilyn yesterday and explain to her what I've been learning from all of you and the joy of being in your midst. And she sends her love and appreciation for your taking good care of me, which you certainly have. This is a hospitable group, and especially I wanted to mention Don, who's taken such good care of me. He just took me in. If you didn't know, I'm staying at his house, and he's just taking care of me. Thank you, Don. And it's a joy to be with you. By the way, he's pretty sharp about this stuff, too. You probably know. He's pretty knowledgeable, and we've had some good conversations. So thank you for the privilege, and let's get right at our subject for this morning. I'm calling this lesson Argument from Complexity. In your series, I called it Design Inference. All of this is about design, isn't it? Design demands a designer. In the course of this series, the elders have said to me, this is a class. So everybody, this is a class. In a class, you can answer questions. And I like to have audience participation. So what was our favorite answer last night, class? That was the answer to almost everything. So folks left knowing how important proteins are. Today, I want to talk about some reasons that you can be confident there's design. And that's what we've been doing all the way through. But let's talk about complexity today. That's the theme for this hour. Before we start that, though, I want to talk about 3 passages of Scripture. And may I say again, in an audience like this, in a church building on a Sunday, it seems fitting to me to start with passages of Scripture as we deal with this subject. But I want you to understand that the primary thrust of what I talk about in this series does not come from this book. It comes from God's other book, which I believe is a grand testimony to what God is. And you'll see that even in these passages. And you'll also see it in what you heard at the first hour this morning. The Apostle Paul used the argument from the world and what it's like to testify of God also. So it's entirely appropriate. Psalm 139 verse 13 says, "For you have formed in my inward parts, you've covered me in my mother's womb. I will praise you, for I am fearfully and wonderfully made. Marvelous are your works, and that my soul knows very well." So, ladies and gentlemen, this morning I want to turn our attention about design to you and your body. And while I'm on that point, there's a wonderful little book called What Darwin Did Not Know by Jeffrey Simmons, MD. And it covers every system in your body. It's about the human body. And it talks about what we've learned about that since Darwin, which is a lot. And it's a marvelous book to explain the complexity and the marvelous and fearfully and wonderfully made bodies that we have. They're a grand testimony. Somebody designed this. Now let's turn to our second passage, which we've used as our theme for this particular series, from Romans 1 and verse 20. I think it's the most powerful expression in the Bible for what we're doing in this series. "For since the creation of the world, his invisible attributes, that is, God's invisible attributes, are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that they are without excuse." How do you see the invisible? Through the things that are made. It's the argument from design, which is what we're appealing to in all of these lessons. And finally, 1 Peter chapter 3 and verse 15. It says, "Sanctify the Lord God in your hearts, and always be ready to give a defense to everyone who asks you a reason for the hope that is in you with meekness and fear." I want to help you be prepared to answer folks who say, why do you believe in God? And is it reasonable to believe in God in the scientific age? The answer is resoundingly yes, and for lots of reasons. I hope by the end of this series you'll have many more reasons to share with folks for your hope in the great God who made us. 1 Peter 3, verse 15. So, complexity. Certainly no one in this room, and I don't think anyone would argue that on this earth, and in living things in particular, there are a massive number of very complex things that are functioning right now. Would you agree? And there's just lots of complex things out there. The question is, where did all that complexity come from? It either came by natural causes, which is what the evolutionist says. Reductionism says complex organs arose from simpler things in small steps by natural causes. You remember I read to you from Dawkins on the first day, blind watchmaker? He believes, ladies and gentlemen, that any complex thing, no matter what it is, can come about by small changes over long periods of time. You just break it down, reduce it to small steps. Each small step could happen naturally. You add up all those small steps and you get a complex thing. That's his answer. Blind forces of physics acted on by natural selection over millions of years, you can get complex things without God. The only other answer I know of is that somebody designed it. If you have another answer to that, would you please come and tell me about that? I've been doing this for 60 years. I have never had anybody come to me and give me any other answer. There are only two answers. Things either came about by natural causes or they were created by something intelligent. And the position is, complex organs could not have arisen without intelligent design. Now, the question I'm going to ask you at this hour is, which of those is more reasonable, given the evidence? And you get to be the jury, because it's going to be up to you to decide that. And I hope you don't let someone else decide it for you. That's my introduction class to this lesson. I want to start then with Darwin himself, who is credited with popularizing for the first time and making it scientifically respectable the notion that complexity could come about from natural selection. Natural selection says that nature by itself will choose those things that are more likely to survive. And by that mechanism, it'll select out of the things that naturally occur through mutations and natural events, the things that can keep growing and developing into something more useful. That's the basic idea. Now, I want to pause right here. If someone asks me, are you an evolutionist? Do you believe in evolution? My answer is yes and no. Like any good politician. Depends on what you mean. If you mean evolution as limited change over time, I'm convinced nature supports that notion thoroughly. If you mean that all living things have come from a common origin of one-celled organisms over millions and billions of years, absolutely, I do not believe that, nor do I believe the evidence of the natural world supports it. I hope you got that. Don't take the position that you don't believe in evolution. You do believe in limited change. If you don't, you're defying a whole bunch of evidence from the natural world. Things do change over time naturally. And Darwin's natural selection explains a lot of things. But it does not explain how all living things got here by natural causes without any designer. Nor does it explain complexity, and Darwin himself struggled with it. Here's his quote from his book, Origin of Species, which I hope you've read. It's only the second most important book in terms of its effect on humanity that's ever been written. The first is this one. But this book has impacted humanity more than any other book, in my opinion. other than the Bible. Because folks have turned to believe in it. Here's one thing Darwin said. If it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down. If you've been in my class, you know when I pause, we just said something important. I want this to sink in. If you're going to believe in Darwinism, natural selection, acting upon natural variation, you're going to believe that things came about by very small changes over long periods of time. Slight. Nature abhors leaps, ladies and gentlemen. Darwin did not believe that you go from a fish to a donkey, boom, in one step. No, sir. He did not believe in saltationism. He believed in gradualism. So his point is, if you could demonstrate there's anything out there that could not have been formed that way, my theory's done. And I would suggest, lest I forget to say it later, if Darwin were alive today, I believe he would say, my theory is done. Because we've learned a whole lot more since the 1850s. So, I want to recommend a book to you. Darwin's Black Box by Michael Behe. There are 2 editions. I would recommend the 2006 edition. It's updated. In this book, he, of course, takes to task Darwinian evolution. And one of the things he does is use an example. He said, suppose now that your neighbor is standing in your yard. And you say, what are you doing in my yard? And how'd you get here? And he would say to you, well, I just jumped over the ditch. And here I am. And you look, and there's the ditch. Maybe that is about 3 feet wide. And he says, I jumped over that ditch. Well, that's believable, wouldn't you think? What if the ditch were that wide? Maybe it's about 6 feet wide. He said, I just jumped over the ditch. Maybe. How about if it's about 15 feet wide? You'd say, I want to see that. You do it again, right? And what if it were this wide? You would say, now, wait a minute. You didn't make that leap. Well, he's a kind of a sharp guy, so he says to you, well, I didn't make that all in one leap. I went from one butte to another. So I made this reasonable jump to this butte, and then to that butte, and then to that one, and then I finally got over here. And you look out there and you say, I don't see that many buttes. And he says, well, after I jumped onto one of them, it kind of weathered away, and it's not there anymore. And you kind of say, I give up. Let's change the subject. The reason he gave this example is because this is very much what it's like in Darwinian evolution. You have to have a bunch of small jumps, right? Little tiny changes. Many of them over long periods of time. If it's a Grand Canyon that requires massive leaps, his theory falls down. So the question is, what about some complex organs? Like the human eye. Let's talk about that one. Darwin talked about that one in his book. And here's what he said. To suppose that the eye, may I use a British accent here? Suppose that the eye, with all of its inimitable contrivances, to focus on different distances, for the admitting of different amounts of light, and for correction of spherical and chromatic aberration, could have been formed by natural selection seems, I freely confess, absurd in the highest degree. Did you get that? All of you know, don't you, that your eye will adjust to different amounts of light? If we turn off the lights here, what happens? Your pupil opens up and allows more light in. Do you have to say, now pupil, open up? No, it just automatically opens up and allows more light in. Everybody knew that in Darwin's day. Or, he said, for the correction of spherical and chromatic aberration. Now, you may not know much about that, and I don't have time to explain all that, but the eye makes some automatic corrections for certain problems. So he knew, class, very well that the eye had some extremely complicated, complex systems that work beautifully. To think that all of that could have been formed by natural selection is absurd. And I say, amen. Then he proceeds to tell you why it did happen that way. He says the human eye is the result of a small set of changes over long periods of time, and that it came about by natural selection, or as Dawkins would say, the blind forces of physics acted upon by natural selection. You can believe that if you like, ladies and gentlemen of the jury. I'm going to suggest to you it has serious flaws. So he said, yet reason tells me that if numerous gradations from a perfect and complex eye to one very imperfect and simple, each grade being useful to its possessor, can be shown to exist. So if I lost you, here's what he's saying. Can you look in nature and find a whole bunch of different kinds of eyes? Some that are way simpler than ours. You find a gradation of eyes in nature. Would all of you agree that that's a fact? Yeah, you can find different kinds of eyes in nature. Secondly, if further the eye does vary ever so slightly, would you agree that you can have variations in eyes? And that the variations be inherited? Look, folks, I wore glasses for a long time. My mom and daddy both wore glasses. I now have had the operation. So I have lenses. And now I have to use these for reading only. It's kind of nice. But the fact is, I inherited from my mom and daddy certain characteristics of my eyeballs. You did too, didn't you? Which is certainly the case, he said. All right, listen to his reasoning. If we can find everything from a very imperfect and simple eye all the way up to a complex one in nature, and if the eye varies a little bit and the variations are inherited, follow. And if any variation or modification in the organ be ever useful to an animal under changing conditions of life, in other words, if there's something about the change that was mutated and adopted and adjusted and passed on that makes you better able to survive, then the difficulty of believing that a perfect and complex eye could be formed by natural selection, though insuperable by our imagination, can hardly be considered real. So when you just think about it in a big picture and you look at human eyes and you think how complicated they are, if you realize there are very simple eyes all the way up to very complex eyes, and each one of them might have had a beneficial effect through the process of evolution, then it's perfectly reasonable to believe that your eyes evolved by simple, small changes over long periods of time. That's the argument. See, one of my goals in this class, ladies and gentlemen, is to help you understand the other guy's position. Everything they say is not stupid. Darwin did not change the world's thinking because his idea was completely ridiculous. It has a lot of sense to it. And it is a very good explanation for limited change. Is it a good explanation for the complexity of the human eye? That's the next question. So the next thing I want to do for you today is to show you a little video clip of a modern day explanation of what Darwin just said. It's a TED Talk. You know what that is? Little brief talks that explain important stuff. So you're about to see a TED Talk on where your eye came from. All right? So, don't go to sleep. All right, here we go. There's the human eye, and here's the TED Talk.
The human eye is an amazing mechanism, able to detect anywhere from a few photons to direct sunlight, or switch focus from the screen in front of you to the distant horizon in a third of a second. In fact, the structures required for such incredible flexibility were once considered so complex that Charles Darwin himself acknowledged that the idea of their having evolved seemed absurd in the highest possible degree. And yet, that is exactly what happened, starting more than 500 million years ago. The story of the human eye begins with a simple light spot, such as the one found in single-celled organisms, like euglena. This is a cluster of light-sensitive proteins linked to the organism's flagellum, activating when it finds light, and therefore food. A more complex version of this light spot can be found in the flatworm planaria. Being cupped rather than flat enables it to better sense the direction of incoming light. Among its other uses, this ability allows an organism to seek out shade and hide from predators. Over the millennia, as such light cups grew deeper in some organisms, the opening at the front grew smaller. The result was a pinhole effect, which increased resolution dramatically, reducing distortion by only allowing a thin beam of light into the eye. The nautilus, an ancestor of the octopus, uses this pinhole eye for improved resolution and directional sensing. Although the pinhole eye allows for simple images, the key step towards the eye as we know it is a lens. This is thought to have evolved through transparent cells covering the opening to prevent infection, allowing the inside of the eye to fill with fluid that optimizes light sensitivity and processing. Crystalline proteins forming at the surface created a structure that proved useful in focusing light at a single point on the retina. It is this lens that is the key to the eye's adaptability, changing its curvature to adapt to near and far vision. This structure of the pinhole camera with a lens served as the basis for what would eventually evolve into the human eye. Further refinements would include a colored ring called the iris that controls the amount of light entering the eye, a tough white outer layer known as the sclera to maintain its structure, and tear glands that secrete a protective film. But equally important was the accompanying evolution of the brain, with its expansion of the visual cortex to process the sharper and more colorful images it was receiving. We now know that far from being an ideal masterpiece of design, our eye bears traces of its step-by-step evolution. For example, the human retina is inverted, with light-detecting cells facing away from the eye opening. This results in a blind spot where the optic nerve must pierce the retina to reach the photosensitive layer in the back. The similar-looking eyes of cephalopods, which evolved independently, have a front-facing retina, allowing them to see without a blind spot. Other creatures' eyes display different adaptations. Anableps, the so-called four-eyed fish, have eyes divided in two sections for looking above and underwater, perfect for spotting both predators and prey. Cats, classically nighttime hunters, have evolved with a reflective layer maximizing the amount of light the eye can detect, granting them excellent night vision, as well as their signature glow. These are just a few examples of the huge diversity of eyes in the animal kingdom. So if you could design an eye, would you do it any differently? This question isn't as strange as it might sound. Today, doctors and scientists are looking at different eye structures to help design biomechanical implants for the vision impaired. And in the not-so-distant future, the machines built with the precision and flexibility of the human eye may even enable it to surpass its own evolution.
First-class presentation, wouldn't you say? That's what our children are being taught. Right, kids? And it's well done. And it's first class. And I might say to you, if you think about it, there's some reason to it, isn't there? One thing I want people to do who are believers in God is not just slough things off as if there is no validity to it at all. You need to think through and be reasonable about it. So let me tell you a couple of things about this TED Talk that you need to recognize. First is, they talk about these all different kinds of eyes as if somehow this one evolved into that one and into that one, right? That's the picture you get. There is zero evidence that the light-sensitive spot in simple single-celled organisms evolved into something else in some other organism. You may have noticed that he also said at the same time that these evolved independently for a couple of these. The evidence, ladies and gentlemen, is if they did evolve, they evolved independently. It wasn't a sequence into which we get one organism that has this nice one and the other ones didn't. It appears that they all evolved independently. That's even worse for the evolutionists, isn't it? Secondly, he threw in a little thing there, which I hope you noticed. There's some evidence that this wasn't designed well, your eye. Did you notice that one? Because your retina is inverted, and the light has to come in the backside, and you also have a blind spot, and they make a big deal out about how that's not good engineering. Now, I don't have the time in this lecture to talk about that, so here's what I want to challenge you to do. I want you to go look up stuff about that very point, and there are solid scientific answers to why that's a better design than in the other way. But did he say anything about that? No. We're going to cast aspersion on the creation view without explaining that there's other explanations that make that reasonable. Don't believe me. You go look and do your own research about that. I want to read you what Darwin said about that light-sensitive spot on the Euglena, single-celled organism. He said, how a nerve comes to be sensitive to light hardly concerns us any more than how life itself originated. Is that an important question? How life originated? It's only the whole matter. Well, how did that first light-sensitive, a simple single cell, how did they get a light-sensitive spot? Well, that doesn't concern us because he thought that cell, a little single cell, is just a blob of albuminous carbon. There's nothing to it. You don't even need to worry about that. Well, I'll tell you what we've learned, ladies and gentlemen. The light-sensitive spot in a euglena or any other one-celled organism that contains it is an amazingly complex system. To Darwin, that little light-sensitive spot was like jumping over a 4-foot ditch. And what we've learned is it's a Grand Canyon. And if you're going to explain it in a Darwinian way, that light-sensitive spot is going to have about 6,800 steps, each butte which has disappeared. You with me? Now, this is heavy chemistry, so I'm not going to explain it all. But to have an advantage, you see, in Darwinian evolution, there has to provide some advantage, right? It's the survival of the fittest. What makes it better? It has to have a sense of light or dark. It has to communicate that information, and it has to be able to react to it, right? I mean, what good is a light-sensitive spot if it doesn't do anything for you? Well, what did he argue it did for that euglena? It gave him direction, right? Light is going to point different directions. So here's what happens with the single-celled organisms. This is an absence of stimulus of light. It just kind of flops around everywhere. It just goes everywhere. It's totally erratic. But when you put light on it, in the presence of that stimulus, it starts going in a general direction. Can you see that? I mean, those are the facts. it kind of goes either toward the light or away from it. Those are facts. So the light-sensitive spot does provide a directivity to that little organism. And how does it do it? Well, it directs the little, what do you call this thing? The flagellum, which moves around. And what you don't know, and what Darwin had no clue about, is to make those things happen like that has chemistry behind it. Here's the bacteriorhodopsin. This molecule is extremely complex, ladies and gentlemen. It's got an end that sticks in outside the cell and an end that sticks inside the cell, and it has an amazing complexity in its chemistry. That's just the rhodopsin. And when the light strikes that rhodopsin, it changes its chemistry in microseconds. You remember how fast that is? But that's not all there is to this. There's another major protein called HTR type. Now you look at the complexity of that thing. Again, it crosses across the membrane. It's got the inside part that's got the triggering domain and the methylation sites and the periplasmic space outside and the ligand-bearing domain. Folks, that is a complex protein, which, by the way, is coded in the DNA and all that stuff I told you yesterday. Both of these work together in precise harmony. So here we have the membrane of that little one-celled organism. Here's the HTR and here's the rhodopsin, and a light strikes it, and it causes this protein to get into action, and it gives us a message to this CHEA. Can you tell I'm skipping a lot here? Which then causes an ATP to become an ADP and remove one of its phosphates and join to that chemical, and then it affects this chemical, which affects that chemical, and this one, which affects that one, and they become phosphorylated, which then sends a signal back to one another. It's a cyclical thing, dear ladies and gentlemen, because listen to me. If light just struck and it went one direction, it would wear out in no time. You have to have it going back and forth. You with me? Or you'd run out of the stuff you need to be sensitive to light. So it's a back and forth reaction that is finely balanced and designed. So it looks like to me. And then they send a message to the flagellum after all of this. And the flagellum then, in turn, either increases or decreases its tumbling depending on the message. But that's not all, class. You got to go back and you got to fix the HTR so it can start over. So there's a signal from the CHEB molecule back to the HER, which allows it to go back to its previous condition, and the rhodopsin as well. Now, I haven't told you 1/10 of what just went on in the chemistry of a light-sensitive spot. So I would say to Mr. Darwin, you better care about where that came from. And that was no small jump, sir. That was a Grand Canyon. How did all that start? And it works like a charm in a little single-celled organism and moves it toward the direction or away from the direction of light. He says, Mr. Behe, that in our age, forget the exterior organ, explain the chemistry. You can't just stand back there and talk about the organ itself as a whole, not anymore. This TED Talk is outdated. They need to get in and explain how this chemistry got started inside the one-celled organism, much less us. And how in turn it directs this amazing thing. Oh, by the way, there's another activity I forgot to tell you about up there. So it directs this thing. Because this is the flagellum. It's a filament that's hooked to a motor that has studs and C-rings, a Slater, a rod, an S-ring, an M-ring, a rotor. It has membranes across here that help it be stabilized. And this is an electrical motor run by chemistry, ladies and gentlemen. That doesn't just happen. There's a motor driving it. And the motor is the chemicals that drive the motor, which we could explain to you in great detail if you're interested. Not now. Are you with me, class? We're only talking about the light-sensitive spot. And the chemistry is amazing. It is no wonder that in Darwin's black box, Behe argues, who is a biochemist and has studied these things in great detail. He says, by irreducibly complex, we mean a single system composed of several well-matched and interacting parts that contribute to the basic function, wherein the removal of any one of the parts causes the system to effectively cease functioning. That's one of the problems with the Darwinian explanation for these complex organs. You take one part of it out, and it stops working. So they've made up some stories about how maybe it was doing one thing or something different for a while, and then it came together and did this. But folks, the way it works requires all parts to work. And it's complicated. So without going back to the previous diagram, you take out the CHEP piece of that, the whole thing stops. And we've done it. So what about us? Well, I told you about the light-sensitive spot. Ours are way more complicated than that. And so are all these other eyes that have been evolved supposedly independently. The eyeball has been studied for a long time. Darwin knew a lot about the physical characteristics of the eye. And all of you do too, I'm sure. You know that there's the cornea and the lens and the iris. There's the vitreous body in here, and there's this thin layer. You see this thin layer here called the optic visual part of the retina, this layer right here that's sensitive to light. Extremely complex. And of course, we could spend days. Do we have any opticians in this audience or optometrists? Anybody here? Well, I've had the privilege of talking to several. And they can lecture you for days about the eye and all the complexities of it. We're going to limit ourselves to the optic nerve today. You see, we can now look at the optic nerve way down with microscopes and other types of equipment to help you look more carefully. Here's the optic layer right here blown up, magnified. And you can see there are rods and cones, there are bipolar neurons, and there are ganglion cells. And here is the blow-up of this section of the rods and the cones and the bipolar neurons. You can see much larger magnification. Light comes in from here, and it's acted upon by the rods and cones. But we can do much better than that. Here's a rod cell, magnified. And notice there's the various parts we've talked about when we talked about the cell yesterday. And look at this, see this piece right here in the rod cell? Here's a magnification of that. And you see all these discs up here, and the mitochondria and the microtubules. It's these discs I'm especially interested in that are down inside the rod cell. And these discs, you see this little piece right here? Is one little piece of these discs blown up over here. Kind of what it looks like. And here's the plasma membrane that has in it the capacity to send a message to your optic nerve. Okay. I skipped about 18 things. Let's talk about this right here. Because what's going on here? This is what allows you to see, class. Here's a blow-up of that. You see these parts of the discs there? And here's the space in between, and here's the plasma membrane, and here's the channels that allow stuff to go in and out. This is the part in Darwin's black box that is split off by little marks where you can skip it. I'm not skipping it. So for just the next couple of minutes, what time is it? 10:30. I've got to finish at 10:40. 10:25. I got to read fast. Listen closely. When light first strikes the retina, a photon interacts with a molecule called 11-cis retinal, which rearranges within picoseconds to trans-retinal. The molecule changes its shape when the light hits it. You know what a picosecond is? That's the length, the time it takes for light to travel the distance of a human hair. Right? How fast does light travel, kids? Anybody remember? 186,000 miles per second. So how long do you think it would take light to cross one human hair? This is how fast this stuff happens. The change in the shape of the retinal molecule forces a change in the shape of the protein rhodopsin, to which the retinal is tightly bound. The protein's metamorphosis alters its behavior. Now it is called metarhodopsin 2, and the protein sticks to another protein called transducin. I should point to this stuff. Here's the rhodopsin. The photon hits it. It changes its structure. It binds with transducin right here. You see that T right there? Before bumping into metarhodopsin 2, transducin is tightly bound to a small molecule called GDP, which is then changed to GTP. But when transducin interacts with metarhodopsin 2, the GTP falls off and the molecule GTP binds to the transducin. The GTP transducin metarhodopsin 2 now binds to a protein called phosphodiesterase, right there, PDE, located in the inner membrane of the cell. When attached to the metarhodopsin and its entourage, the phosphodiesterase acquires the chemical ability to cut a molecule called cGMP, right there, and it turns into 5-GMP, so you're reducing the concentration of cGMP in this medium. You see it right here? You're reducing that. It's kind of like pulling the plug in a bathtub. The water goes down. So far, so good? Quiz tomorrow? Another membrane protein that binds cGMP is called an ion channel right here. That channel is the gateway that allows sodium and calcium ions to come in. Sodium ions and calcium ions are allowed to come in. When the cGMP concentration decreases, that channel closes, which causes an electrical charge that builds up, that is then sent to the optic nerve, which goes to your brain, which interprets it as three-dimensional pictures with color. You think there's chemistry involved in that whole process? Class, if that's all that happened, you would be blind in 5 minutes. Because the whole system would be out of whack. So what your eye automatically does is it starts reversing what just happened immediately, so that you keep in balance the system that is required for you to see. And is this system anything like the light-sensitive spot system? Well, it is in the sense that it's cyclical, but it's completely different chemistry. Tell me, Darwin, how did this come from that by small changes over long periods of time, both of which function independently of one another and beautifully? I think, beloved, they were independently designed by a master creator. But here's what happens. First, in the ion channel, which also lets calcium in, when the cGMP level falls, the phosphodiesterase enzyme, which destroys GMP, slows down. So this thing slows down. Secondly, there's another chemical called guanylate cyclase down here that starts producing more cGMP. So it allows the concentration of this stuff to go back up again, which causes all these reactions. I'm not going to read all this. It's causing them all to go backwards and reproduce what they had before. Because you got to get your rhodopsin back. You got to get your transducin back. So these two substances up here start reacting immediately to get your rhodopsin back and your transducin back. Folks, it's like this happening in picoseconds. You've been watching me up here. And your eyes have watched me doing crazy things. And you've seen everything I've done, haven't you? They do it automatically. You know why you've been able to watch for me 30 minutes? Because of this. And what Mr. Behe would say to Mr. Darwin, forget the cornea and the lens and the outside stuff that y'all talk about all the time and explain this to me. You tell me how the chemistry started happening and evolved by small changes over long periods of time, and then I'll talk. And I suggest to you, class, you go research the stories that are made up about how this evolved. It is a bunch of fairy tales. It's the myth of the century. Here's that system of back and forth. The cGMP becomes 5GMP, but immediately it starts being produced the other way. So whereas it closes up here, it opens down here, and things are in constant designed balance. So Behe, toward the end of his book, says this. These scientific obstacles, because he doesn't just talk about the eye, he talks about the operation of that flagellum in great detail. He talks about blood clotting. You ever studied blood clotting? Folks, that's one of the most amazing systems that works in your body constantly. And it's a cyclical system. When your body gets cut, it goes into immediate reaction to close that thing up, called blood clotting. And the process is automatic. But you ought to see the chemistry, class. It's 1, 2, 3, 4, 5, 6, 7, 8, 10 steps that cascade to close that thing up. But people, if that system continued, you'd clot to death. Have you thought about this? Your body has built in a process to reverse the clotting process when it needs to be, so you don't clot yourself to death. Are blood clots dangerous? Well, they kill a lot of people. You call it what? Heart attacks and strokes. 2 of the biggest killers there are. So clots in the wrong place are very bad. Your body does it all the time by a balanced system. Now, it can get out of whack. Things can get mutated or things can change in your system, and when it does, you die. But blood clotting is another thing he describes in this in great detail. It's fascinating reading. So he says these scientific obstacles serve as stark examples of the mountains and chasms that block a Darwinian. What he means is, it's not a 4-foot ditch, ladies and gentlemen. Every one of these is a Grand Canyon. So how'd you get from here to there? Oh, I jumped to this butte and this one. And you say, well, where's the evidence? Oh, it went away. Because the evidence isn't there. The result of these cumulative efforts to investigate the cell, to investigate life at the molecular level, is a loud, clear, piercing cry of design. Have I been saying that all weekend? The result is so unambiguous and so significant that it must be ranked as one of the greatest achievements in the history of science. The discovery rivals those of Newton and Einstein, Lavoisier and Schrödinger, Pasteur and Darwin. His question is, the observation of this intelligent design of life is as momentous as the observation that the earth goes around the sun, or that disease is caused by bacteria, or that radiation is emitted in quanta. The magnitude of the victory gained at such great cost through the sustained effort of the course of decades would be expected to send champagne corks flying in labs around the world. This triumph of science should evoke cries of Eureka from 10,000 throats. Why don't we say it? Eureka! Say it. Folks, we have discovered the complexity of living things at the molecular level in the last 60 years. And there is nothing to explain it from a Darwinian point of view, I'm telling you. It should occasion much hand-slapping and high-fiving and perhaps an excuse to take a day off. And then he says, but no bottles have been uncorked, no hands have been slapped. Instead, a curious, embarrassed silence surrounds the stark complexity of the cell. When the subject comes up in public, feet start to shuffle and breathing gets a bit labored. In private, people are a bit more relaxed. Many explicitly admit the obvious, but then stare at the ground, shake their heads, and let it go at that. So one of our questions over this series was, why do people believe in the Darwinian theory? Here's his answer. Why does the scientific community not greedily embrace its startling discovery? Why is the observation of design handled with such intellectual gloves? The dilemma is, and by the way, prior to this, he talked about coming into a big old empty room and everybody's on the floor looking around and there's an elephant in the middle of the room. And everybody's looking around. And they don't see the elephant. And he says, the dilemma is that while one side of the elephant is labeled intelligent design, the other might be labeled God. And for many of our scientist friends, that is not allowed. So we don't see that. And I can read you quotes of those who say that specifically. We will not allow God's foot in the door of the science classroom. Which means, ladies and gentlemen, you have excluded the only other answer to how things came about before you ever start. I think I could win a debate if there's only one answer. And I can just make up stories to make it supportive. That's not good science. And while I admit science cannot ultimately investigate God, his attributes are beyond science, they can certainly investigate intelligent design and admit it, because the evidence is everywhere. And then I would say to you, ladies and gentlemen, if you want to know more about who designed it, you need to go to this book, which I'm convinced our God has revealed to us so we can know him better and learn what he wants us to do. Wouldn't you want to know that if you believed he made you? And I'm convinced he made us in his image, and that we are not different in degree from all the other animals. We are different in kind, because we are made in his image, after his likeness, and have given some of his characteristics. So I close this talk by saying there are many reasons for our hope for examining the natural world, in examining the natural world. 1 Peter 3 is abundantly easy to respond to in this exciting scientific age. I hope you see that, and I meant that. I hope you see that. Thank you for your good attention at this hour, and we'll turn it over now. I finished a little early, folks.